Okay, so now let's look at a couple other results from Mileti's textbook, but now on the part on compactness, but for first order logic. Okay, so this is section 6.3, page 157 in Mileti's textbook. Now we are compactness for first order logic. Review what that is. It's right here. If every finite subset of gamma is satisfiable, then gamma is satisfiable. So same statement as the one for sentential logic, except that satisfiable now means something else, right? Satisfiable before meant there exists a truth assignment that makes all the formulas true. Here it means that there is a structure that makes all the formulas true. Okay. So this is what I want to look at. This is short proposition right here. Proposition 3.6 in chapter 6. So let K be the equivalence, be the class of all equivalence classes. Sorry, of all equivalence relations in which all equivalence classes are finite. The statement says this class is not an elementary class in the language R. Okay, so few things to comment here. First, elementary class, if you look back, he uses a different notation than Enderton's. Elementary class for him means there exists a set of formulas that axiomatize a class, not necessarily finite. He calls them strongly elementary when there's a finite one. While Enderton, elementary means there's a finite set of formulas axiomatizing the class, and the other ones are called widely elementary, the ones that you allow infinite classes like this. So what does it mean, the class of all equivalence relations in which all equivalence classes are finite? So we are in first order logic now, so we are representing these structures as structures in our language. And here it's saying that the language has a unary predicate R. So usually if you're talking about something like this, it's because before in the textbook there were a few examples dealing with equivalence relations. So it's worth looking at them and see how that's being represented. But in this case, you can probably figure it out, right? So what is an equivalence relation? An equivalence relation, you have a set, a domain, and you have a relation between the elements which satisfies the properties of being an equivalence relation. So that means this R here is going to be the relation, so it has to be a binary relation. And this relation on the set, the domain, is going to be the universe of either a structure. This relation has to satisfy the properties of being an equivalence relation, namely that it's transitive, reflexive, and symmetric. That's what makes an equivalence relation. Okay, so let's. So it's saying that if you take the class where all equivalence classes are finite, if you don't remember what equivalence class is, go and look it up. It's not elementary, so it cannot be a set of formulas axiomatizing that. Okay, so let's go into the proof. Suppose that sigma, subset of cent L. So here again, you have to look at the notation in the textbook. If you don't, if you haven't read the textbook before, L here refers to what we usually call the vocabulary. Usually we are using the letter tau for the vocabulary. Mileti uses L, fine. And cent L, if you don't know, if you either you look it up or you can guess pretty much that it means sentences. This is sentences in the language with vocabulary L, which only contains the relation R. Okay, so sentences in the relation R, such that the class K is a subset of mod sigma. Mod sigma, I think we defined this in class. So you can look it up in our notes, or again, look it up what it means. It's a set of all models of sigma. So a set of all structures that are models of all the sentences in sigma at the same time. Okay, so this is what it's doing. I mean, we're trying to show that there is no set of sentences whose models are exactly K. And he's saying, okay, suppose we have one that it It's a superset of k. And what are we gonna do? So we're gonna extend the language. So with vocabulary, now we make it a bit bigger, and we add to it C. So where C is a new constant symbol. Okay, so essentially you can write this down if you want. So the new language contains two symbols, R and C. And C is a new constant symbol we hadn't seen before. And then what are we gonna do? Okay, so for each n in the positive natural numbers, let tau n be the sentence in the new language with L prime that says the following, and then we have to parse what it says. There exists x1, x2, xn such that, remember, this is a conjunction of a bunch of formulas, like a finite conjunction of many formulas. It's a kind of a shorthand for that. Whenever you have I and j between 1 and n, and I strictly less than j, so they are different, the xi and xj have to be different. So that means whenever you have n elements, all of them different, no, there exist n elements, all of them different, which also satisfy that they are related to C. And again, that's a funny, weird relation, which you should either look it up, or that's in the class we've been writing these as R of Cxi or C Rxi. Those are all the same thing. I guess you can guess that. So this is saying that there exist n elements, they're all different, and they are all related to C via their relation. So it's saying that there are at least n things that are equivalent in this equivalence relation to C, in the same equivalence class as C. And we let sigma prime is now the same set of formulas of sentences that we took before, which we were assuming that those models, their models contain all the models of this class K, and we add all these guys. Okay, we still don't really know where we're going. I mean, we kind of guess it because it was a similar format as the one before. But let's see where it goes. So we claim that every finite subset of sigma prime has a model. Okay, so that will guarantee, we know from compactness that sigma prime is going to have a model, and that's probably going to be useful. Okay, so let's see why that claim is going to be used, why it's true. So consider a finite subset, that's kind of what you expect, of sigma prime. Finite subset must be a subset of all of sum of sigma, so in particular a subset of sigma, and it must be a finite subset, contain a finite subset of these guys. So it says fix an n such that you're a subset of these. Okay, so that makes sense because it's finite, so it's finite subset of both. So there is a bigger n. So notice that if we let n prime be the number from 0 to n, and Rm prime, so this the notation we're using so far is that this means R as interpreted in a structure M prime, and the Roman letter means this is the domain of the structure, right? So this is a relation on M prime square, also on this guy's square. Well, it's actually equal to a square. So this relation contains all the pairs for M prime. So is it an equivalence relation? Yes, because everybody is connected to everybody. That's a trivial equivalence relation. Everybody is equivalent to everybody. And we let C be 0. Then M prime is a model of sigma 0 prime. Okay, so let's look at this. First, it'd be good to write this in the notation you used to write it usually. So you would write M prime with the calligraphic M is equal to, has domain M, Roman M prime, which is this one up here, all the numbers from 0 to n. This is a finite domain, and it has the relation R M prime, which is all the pairs. It contains all the pairs from M prime, and it contains a constant is being interpreted as the element 0, which is just some element. And it says it's a model of sigma prime. And why is it a model of sigma prime? Well, we have to see why. Well, first, it needs to be a model of sigma. And why is it a model? We don't know anything about sigma. All we know is that the models of sigma contain the whole class K. And this model belongs to this class K. Yeah, so class K is a class of equivalence relation in which all equivalence classes are finite. We said this is a trivial equivalence relation, and it has only one equivalence class, but it's finite. Only these guys. Okay, so it belongs to K, so it satisfies sigma. And it satisfies these guys that said that the equivalence class of n of C has size at least n for all little n below capital N. And yes, the equivalence class of C here is 0. Equivalence class is everything, so it has n plus 1 element. So it's good, so this one satisfies sigma 0 prime. Cool, and then you continue on reading. Thus, every finite subset of sigma prime has a model. We just proved that because see, this one was arbitrary. So sigma prime has a model by compactness. That's what compactness says. Okay, now if we restrict this model to L, and I guess again we have to look at what this word restrict means here, but it means what? Let's just figure it out. Well, this is an L prime model because it has a relation R and a constant for C, thus interpreting C, right? And L has only one relation, right? So L prime has these two and L has these. So restricting the model to L means forget about C, just consider the relation R. Well, not for this model, for the model that is a model of all of sigma prime. If you restrict this model that is a model of all of sigma prime to L, we get an element of mod sigma. Yes, because that's what we chose. We chose something that satisfies all of these guys, so it satisfies sigma. And it's not in the class K. Why is that? Because it has an infinite equivalence class. And why is that? Well, I have to see why is that. Well, the class, this model, let's call it something else. So it's not M prime. This model is going to be, M prime is going to be, let's call it, no, sorry. Let's call it something else. We have n prime, which has a domain n prime, relation R, and a constant C, interpreted in n prime. This one models all of sigma prime, and then we are considering n, which is the restriction, so that means n prime R n prime, but without the constant, just those two. And this one models, well, not all of sigma prime, because these taus in sigma prime talk about C, so we couldn't talk about them because we forgot about the constant C. But the part of sigma doesn't use the constant C, so it does model sigma. So that's why we have this. So if you restrict the model L to only, if you restrict the model n prime to only this relation R, we get a model of sigma, and it's not in K because it has an infinite class. Why is that? Well, this constant C that existed before, I mean, now it's not a sign here, but it's still an element. We kept the same domain and we kept the same dimension. It's just that we forgot the interpretation of C. It's the same structure without an interpretation for C when we restrict. We keep the same n prime and the same relation, same model, so same equivalence relation, except that we forgot who is the constant C being assigned. But there is this is still here, and this constant C is assigned to somebody which has an infinite equivalence relation because it satisfies equivalence class, because it satisfies all these formulas, right? So the equivalence class of C must have size at least n for all n, so it has to be infinite. So that equivalence class is still gonna show up here. So this one here has an infinite equivalence class, so it does not belong to K, because K is only the ones that have finite. All equivalence classes finite. Okay, and then here he's putting the box. The proof is finished. Why is it finished? Well, we want to show that K is not an elementary class, we started by just taking any sigma whose models contain all the class K, and we ended up proving that for every such sigma that there must be a model of sigma which is not in K. And that implies that the model of sigma cannot be equal to K. There always has to be something here not in there. So whatever we choose for sigma is not, the class of its models is not going to be exactly K. And that's why it's not elementary, because we cannot have any sigma whose models are K. Right? So that's what this says. Good. So yes, again, that's how you read these proofs very slowly. For each sentence, you stop and figure out why is this true. Draw a little picture, see how it matches the notation that you learn in class, that you know. Write a few things, mark things around. Each line, why is it true? Okay, we'll do one more, and then that will be it for this week. See you next week.